Nice weather, huh? I thought we were done. With all this rain. If you remember from last time, we talked about sequential least squares via a very simple problem. So what we did was a very simple example, which was you had x plus noise, and you had n data points, and then you got a new data point, and you wanted to update. And what we saw was the estimate of a hat after n iterations, or after n data points, is the previous estimate plus a correction. This k of n is a gain, basically, minus a hat n minus 1. Okay? So this is what we call the gain. This is what we called the innovation. Another name for it was residual, prediction error, and so on. The idea is that this term is just a correction. And the correction had to be such that this gain is in fact less than 1, otherwise this sequence, thought of as a dynamic system, wouldn't converge to the right answer. It would just blow up. And we also talked about how you could track not only the value of the estimate, but also an uncertainty around the estimate. So the variance of a hat n is 1 minus this gain times the variance a hat n minus 1. And this also shows you that because this gain is less than 1, then this sequence eventually converges as well. Okay, so this coefficient in front is less than 1, so therefore the variance decays with more and more data points. Okay, so there's a couple of things we didn't talk about with respect to this, some very simple things, but which turn out to be important. One of them is that whenever you have an iteration of this sort, or iteration of any sort, you have to think about initializing that iteration. Okay? So if you had to write this down, what would you set for, what would you set for a hat of 0? All right? Well, a pretty simple thing to do is you just set that to be the first data point, or 0th data point. Okay, and what about the variance of a hat 0? You have to pick something for that, and you can pick that to be some number. And as you'll see, the effect of these things will be felt, but hopefully not for very long. In other words, what you want is you want the accuracy of the estimate at the end not to depend ultimately on what you guessed as your first estimate. Okay, so you want this effect to eventually decay away, so that you're really making use of all of your data. If you set these numbers in such a way that your estimator, as a function of iteration, gave a huge weight to that first guess, then you're not really using your data in a very efficient way. And you'll see that more clearly in the next generalization of this. So having that, now let's talk about the general sequential linear least squares. Okay, and I emphasize this is just for the linear case. For the nonlinear case, we will just talk about the nonlinear case right after this, but the iterations will be very similar to what I'm talking about here. The only difference is that you will typically end up taking a nonlinear problem and approximating it with a linear problem, and then running this forward. And then at every iteration, when you come up with a new estimate, you have to relinearize the problem, and so on. Okay, so let's take the following scenario. So the idea here is that you have some x, which is a vector, looks like this, okay? And this x is going to have some length, and let's say for the time being, we write it as x of 0, x of 1, x of n transpose. So this is a column vector which has n plus 1 terms in it. Okay? And if you remember, when we wanted to solve the least squares problem, we minimized the quadratic cost function with possibly a weight in the middle, which gave us what we call the weighted least squares. So let's just write that general format. So in order to estimate theta hat, we wrote minimize over theta x minus h theta transpose some covariance C inverse times x minus h theta, like this. Okay, and with this in place, our weighted least squares estimate given this data is h transpose C inverse h inverse h transpose C inverse x. And the covariance of this estimate, weighted least squares, h transpose C inverse h inverse. Okay, which is simply this piece here. Okay. So to make things simple, what I'm going to assume is that this covariance matrix is diagonal. In other words, that the data points x1 or x0 through xn are not correlated with each other, but I'm going to let the variances for these be different. So this is a special case. Let C be equal to sigma 0 squared, sigma n squared, 0 squared. Okay? In the other case, if the off-diagonal terms are not 0, the analysis that I give you is equally valid, except for the fact that the math becomes a little bit more messy. Okay. So now let's take a look at the structure of this matrix H, and let's write it with an index indicating that we have x0 through xn, so there's n plus 1 data points. So if you write this, what you have is h n minus 1. This is the matrix that you would have for the previous iteration, and then you add an extra row. Okay, and this extra row we can denote it as h transpose of n. Okay, so as far as dimensions are concerned, this matrix H here, this guy would have dimension n by p. Okay, this here is 1 by p. And this matrix here, this part, h of n minus 1, corresponds to data up to index n minus 1. Okay, and of course the dimension of this guy would be n plus 1 by p. Okay. So let's take a look at what we're doing with our data now. So let's write this data in just so on, x n minus 1, xn. So the idea here is that you're going to take these data, which correspond to hn minus 1, and from these you're going to produce an estimate, which is theta hat, and we're going to index it with n minus 1. And then what you want to do is then take the whole data, including this additional one, and compute a new estimate, theta hat n. Okay? So we can rewrite all of this stuff and multiply things out, and the bottom line is the estimate after n data points is the previous estimate plus the gain times the prediction error, which in this case is x of n minus h transpose n times theta hat n minus 1. Okay? So again, this is the prediction error, and this is the gain. So fundamentally, this is the same as what we saw before, except for the fact that the definitions for the gain and for this term are a little bit different. And I'll tell you what they are in a minute. But at this point, it's worthwhile stopping and taking a look at your model that we started off with from the beginning. Remember, corresponding to this whole thing was this matrix expression h theta plus error, right? And if you write one of these data points, if you write one of the elements of x, let's say write xn, right? The nth data point is what? Is h transpose n times theta plus e of n, right? So if you look in here, this is exactly the difference between these two terms if theta is replaced by theta hat n minus 1. So that's why we call it the prediction error. Okay? And in fact, this h transpose is precisely that last row that we added to this whole expression. Okay, so what does the gain look like? Before I tell you what the gain looks like, let's write down the covariance of theta hat n. This is for any iteration. This is h transpose n. I'm going to give this guy an index too. Cn inverse hn inverse. The reason I'm giving this guy an index is as you get more and more data points, then you just add one additional diagonal element to this matrix and just make it bigger. Okay? Nothing special there. So this is the covariance, and this is just shorthand. We're going to call this Sn. Okay, so this is not terribly different than what you saw before. This covariance is well understood. Then it turns out the gain, in terms of this covariance, looks like this. Kn is S n minus 1 hn sigma n squared plus h transpose n Sn minus 1 hn. Okay, now I haven't done a derivation for you from this, but the let's give you a rough intuition for why this is the gain. Well, first of all, you notice that this gain is a scalar, which is why I'm able to write it like this. So what I was saying earlier is that if you wanted to do this for the more general case, then the gain would also turn out to be a vector or a matrix. So here it's just simpler to write it down because it's a scalar. All right, so let's take a look at this. If you look at this expression here, what you see is that the gain is basically somehow a normalized version of the uncertainty from the previous estimate. Okay, so you see an expression here that looks like what you have in the denominator here. Okay, in fact, if you rewrite this so that you were to invert this side, you write this as an S inverse, then what you see here is K is basically telling you how much weight to give this new data point. Okay, so if you look at this expression here, you have the new estimate is the old estimate plus some kind of correction. What does that correction depend on? It depends on the new data point, right? So if the new data point is more reliable than the estimate that you already have, this part should get a larger coefficient in front of it, and that's what this is telling you. Okay, so in the numerator, you have the basically something related to the covariance of the last estimate, and in the denominator, you have the same thing plus the variance of the new estimate. So the size of this guy gets bigger or smaller depending on the balance between the information you got from all the other data points and the information you're getting from this new data point. Okay, so that's the more or less the intuition behind this. Now, if you want to run this whole thing forward, again, you have to initialize all of these variables. So how do we do that? Well, in the way we have written this iteration, let's go down for a second. Okay, so this iteration here, if I want to have theta hat of 1, then I need theta hat of 0. If I want theta hat of 0, I need theta hat of -1, and so on and so forth. Okay, so if you want to start this at n equals 0, which is your first index here, then what you need to do is to set two values. You need to set theta hat of -1. And you also need to set some covariance for this, because you need s of n minus 1. So you need to set s of -1. Okay. So first of all, how do we start with this? Well, theta hat of -1 is, you're trying to come up with a guess for what theta is before you have any data. Right? So actually it shouldn't matter. You can set it to be whatever you want. The effect will disappear, so let's set this to be 0. Okay, simple enough. Now this guy, what should we set this to be? Again, we don't know what to set s to be, s of -1 to be, but a simple choice for that is just to set it to be alpha times identity. Okay. Now what about alpha? Why an alpha there? The reason I put an alpha there is because I want to tell the estimator that my first guess is just a guess. I really have no idea what theta is at this point. So when I set an alpha there, what I want is I want this alpha to be a very large number. Okay. In other words, I'm very uncertain about what this guess is, and so I want you to just take it as a way to start the estimator and then forget about it very quickly. And this is going to allow me to do that. Let's take a look at what happens to the gain at 0. So k of 0, if I stick these numbers in here, what I get is alpha h of 0 times sigma 0 squared plus alpha h transpose 0 h of 0. Okay. So now let's say I let alpha get very large. If I let alpha go to infinity, then what happens to k of 0? Then this goes to 1, right? Because regardless of what sigma 0 is, I have two very large numbers, so this goes to 1. Okay. On the other hand, if I set alpha to be small, then what happens to the gain? The gain goes to 0, right? Okay. This situation is not desirable. The reason why it's not desirable is because if the gain goes to 0, this is a situation where basically the filter stops working. It stops doing anything. In other words, it no longer will take into account the next data point that you give it. Why? Because you've set alpha to be so small in here. What does that mean? It means you have a huge amount of confidence in the starting guess that you gave it. And if you have a huge amount of confidence, the filter will comply. We'll say, okay, well, I'll ignore the data. Okay? So this is what happens. Now there's a funny story, a very real story that is behind this, or related to this. And this is the Apollo moon landing. Okay, yeah, everybody knows about this, right? The first time people landed on the moon. So there was a lunar module that was supposed to land on the surface of the moon. And the story is that it was supposed to do it automatically. Okay? And it was supposed to do it using basically a more fancy version of all of this stuff, which is, as I mentioned, the Kalman filter. And apparently somebody forgot to set this alpha a very large number. And so what ended up happening is that they were coming for the approach, and they noticed that they were approaching the surface of the moon at an alarming speed. Right? They were going to just crash into the surface of the moon. And so the Kalman filter had stopped tracking because they hadn't set this alpha large enough. And so what ended up happening is they disengaged the autopilot and they landed the lunar lander by hand, okay, successfully, and nobody died. So, you know, when I particularly when I talk to my kids and you know, they're doing some math and they make a small mistake, and they say, oh, but it's just a small mistake. Well, yeah, you know, if you're an engineer, a small mistake can kill people, right? So you have to check your numbers. Okay. All right, so as I said, unfortunately in this course we don't have a whole lot of time to get into the details of things like the Kalman filter, but the spirit is the same. In other words, here what you saw, let me just step back for a second. The formulation that we have is a very simple one. We started with the least squares. And the reason we started with the least squares is because the equations come out to be very tidy and nice. Now, if it so happens that instead of this, what you have is you want to minimize a likelihood function, right? So let's say you want to do maximum likelihood estimate, okay? So you can write an equation like this, except that it won't be a quadratic. It'll be the log likelihood function that you're minimizing. Therefore, it will not be a quadratic function of the error estimate that you don't know. It won't be a quadratic function of the unknown parameter. It'll be some other function. Its minimization will not necessarily be in closed form. But still, you can do things like compute an estimate, compute the covariance for the estimate, and then try to see if you can write that estimate in terms of the previous one. And it turns out you can in most instances. And if you can't, then you linearize to write something like this. And so what you end up carrying with you forward from iteration to iteration, from index to index, is both the estimate and the probability density for the estimate. Okay, here what we did is we simply carried forward the estimate and the covariance of the estimate, because that was all we cared about, right? Now, if the density is something specific and you can't do least squares in this simple fashion, then you carry forward not just the first and second moments of the estimate, but the entire probability density. Now, updating a probability density from iteration to iteration is a very difficult thing to do, and it requires huge computational power typically. Okay, so lots of things have been developed for doing these things. Monte Carlo, Markov chain Monte Carlo, and various other computational methods have been developed for updating these likelihood functions. Okay, same thing applies if you want to do maximum a posteriori. Okay. Again, some cost function, you minimize it, you compute the estimate, you compute the PDF of the estimate, and then you carry those forward iteration by iteration. Okay. As I mentioned to somebody, you asked me, I guess, last time, we can have an entire course on sequential estimation. In fact, when I was a PhD student, I had an entire course, not a quarter, but an entire semester on sequential estimation. And if you want to see what the details of that are, I'd be happy to, I'll just give you my notes from when I was a student. It's a fascinating subject, but it really is one that we're not really doing much justice to. But if you're interested in the details, if you want to know more about where to go, what to look for, papers, books, etc., I'd be happy to direct you to the right resources. Okay, so now let's just get back to the general nonlinear scenario. Suppose we want to stick with the least squares formulation, but then suppose that our problem doesn't in fact lend itself to such a simple setup. So let's just do nonlinear least squares, and I'm not going to do this iteratively. I'm just going to do it for just the batch setup. So I'm going to take all the data and come up with one estimate, and then you'll see you can take that and iterate it if you want from data point to data point as well. So suppose we have a model like this, plus error, and this guy is just 0 mean. Okay, so this theta might be multiple parameters that we don't know. And the data that, this data is a parameter we don't know, and n might go from, let's say, 0 to n minus 1. Okay. So let's take this and stack it all into a vector as normal. So we write x equals s of theta plus e. Now this s is itself a vector. It's a vector function of a vector parameter. Okay? You have a bunch of s's for 0 to n minus 1, and you have a bunch of thetas, theta 1 through theta p, let's say. Okay? All right, so with this setup, then what we can do is write a standard least squares problem, except for the fact that in this case it'll be nonlinear. And it will look like this. So I'll write x minus s of theta transpose times some weight times x minus s of theta transpose. Okay? And I want to minimize this with respect to theta. Okay, so again, this is the difference between x and s of theta. And I put some weight in here, but this is just the general weighted nonlinear least squares. For simplicity in what I'm going to talk about, I'm just going to set w to be identity, but you now see how it all works, right? You can just absorb, turn w into a square root. This is going to be a symmetric, positive definite matrix. Okay, but for now, I'm just going to let w be identity. Okay, so let's write this j of theta, x minus s of theta transpose times x minus s of theta. Okay, and we want to minimize this with respect to theta. So we take the derivative, set it equal to 0. And what we get is x minus s theta transpose ds d theta equal to 0. Okay, now this, you have to be a little careful when you write this down. This here is a vector. Okay, this is what we typically refer to as the gradient, because it's a multidimensional derivative. Okay, so you have to be a little careful writing that down. But in any event, this looks a lot like something we dealt with before. So you can write this function here. You can just think of it as some g of theta equal to 0. Okay? This is just some probably pretty ugly algebraic equation in terms of theta, and you want to solve this equation g of theta equals 0. Now we solve this. One way that we did it was using Newton-Raphson. And the idea was theta k plus 1 theta k minus e.g. d theta inverse g of theta, and this evaluated at theta equals theta k. Okay, so this is just a vector version of the Newton-Raphson that we talked about, where this guy here is now a matrix. Okay? So g of theta is a vector function. Now you're taking that vector function and you're differentiating it with respect to the elements, and you're going to get something like this. Okay, so this is one way to do it. It's a perfectly reasonable way to do it. You run this iteration forward, and as long as this guy here is well behaved, you're going to converge to something. Okay. Now there's two problems. One is, what exactly are you going to converge to, and two, how fast are you going to converge to it? Okay. So one of the things that happens is that typically when you have problems like this, there's going to be multiple thetas for which this is satisfied. Okay. And so in the scalar case, I showed you that you would have the g of theta crossing 0 multiple times. Well, here it's not even one-dimensional, it's multiple dimensions. So you have lots of opportunities for finding what we call local minima to this cost function. And so depending on how you initialize it, you're going to end up with possibly something that is not the best solution. And furthermore, this guy here might be ill-behaved, and therefore you might expect some problems. If you know, if you're doing this and somewhere this becomes very small, then what that means is that this cost function is very flat, and so you're not going to have a very good time converging in a reasonable number of iterations. So people have looked at many other ways of solving these problems, and one of them, which is actually sort of intuitively more friendly, is the so-called Gauss-Newton. The Gauss-Newton method. The idea behind Gauss-Newton is to do a linearization, not of, so if you remember this g of theta that we got, we did something with the original cost function. Here, what we're going to do is we're going to try to generalize, we're going to try to really linearize s of theta. Okay. S of theta is a nonlinear function of theta. So here's how we do it. Around an initial guess, let's say theta 0. So in the scalar case, this is this would be, let's just use the Taylor series. Okay, so this would be S and theta 0 plus derivative evaluated at theta 0 times theta minus theta 0. Okay, so this is a first order Taylor series expansion. I've completely ignored all the higher order terms. I can do that because I'm assuming theta 0 is small, theta minus theta 0 is small enough. In other words, theta 0 is close enough to the right answer that if I square this and cube it and so on, they'll just get smaller and smaller. Okay, so here's what we do. Now, if you take your j of theta and write it in explicit form, you have n equals 0 to n minus 1, x of n minus s of n theta squared. So this is just another way of writing this quadratic. Okay, it's just the elements squared. Then what you do is, instead of minimizing this, you minimize an approximated version of this, where s is in fact replaced with this linearization. So here's what it looks like. N equals 0, n minus 1, x of n minus n theta 0 plus dst theta evaluated at theta 0 times theta minus theta 0, and then the whole thing squared. Okay. So if you look at this now, what you'll notice is that, well, s of n and theta 0 is going to be known, right? So this is just something that you can absorb along with x of n. What's not known here is theta. And now if you look at this whole cost function, something convenient has happened. Namely, you started with a cost function which is nonlinear here in theta, and you ended up with a cost function that is now quadratic in theta. Okay? So now we can minimize this and get an estimate for theta. Okay? So let's see, how do we do this? All right, so I'm going to go back to writing in terms of the vector notation. So what I'm going to do is write h theta 0. I'm going to define this vector like this. d s1 theta d theta, so on, d s and minus 1 theta d theta. Okay? And then s of theta 0 is a vector. It will be s of 0 theta 0, s of 1 theta 0, and so on. S of n minus 1 theta 0. Okay? So with these two definitions, what you have here is basically a linear least squares problem where the unknown is theta. Okay? So if you solve this linear least squares problem with this definition, what you get, let's just do it for one step. So once you've done this for theta 0, what you get is theta 1 hat, this is the next estimate, is theta 0 hat plus H 0, H theta 0 transpose H theta 0 inverse H theta 0 transpose X minus S theta 0. Okay? So this is basically very much like the least squares solution that you had before, and this is just the prediction error. Okay, so you keep repeating this. So you get this new estimate, theta 1, and now you go back to this expression, to this guy here, and you relinearize the problem in terms of theta 1. You get a quadratic cost function in terms of theta. You solve it again, you get a least squares type formulation, and then you just update. Okay, so in general, then what you have is theta hat k plus 1 is theta hat k plus h of theta k transpose h theta k inverse h theta k transpose times x minus s of theta k. And this s theta k here is defined in the same fashion as these. Okay. All right, so let's go back for a second to this. We could have also just taken this j of theta and directly linearized it. We could have approximated j of theta around some theta. That's also possible. It gives you another algorithm. Okay. S of theta linearized in this fashion gives you what I called the Gauss-Newton method, which gives you a linear iteration, which is very simple and straightforward to carry out. What you notice here is that everything you're doing is simple matrix vector multiplies. So this H is just a matrix, just like the H that you had for the linear least squares problem. And furthermore, one thing that you notice is that the convergence is to the right answer, because if you look at this as k goes to infinity, what's going to happen is that these two terms have to become equal, right? So if these two terms become equal, then this is your solution, okay? And once you rewrite this solution in terms of what it ought to be, set this equal to 0 and solve, what you'll see is that it's essentially equivalent to going back and linearizing the j of theta from the beginning. Okay, so you end up getting the same answer, but you get a different path. You take a different path to get to that final answer. One thing to keep in mind, however, is that this iteration, as long as these guys are well behaved and so on, will converge. However, there's no guarantee that you will converge to the global minimum of that cost function. Okay? So in general, there is no guarantee that convergence will be to the global minimum of this j of theta. And as I said, this is because it depends on where you start. Okay, so there are various tricks that have been invented to deal with this. One of them is you basically start this iteration with a whole bunch of random choices of theta. Okay, and then let them converge. And you pick the one that gives you the smallest j of theta at the end. That's one way to do it. Another way to do it is that you might have an idea of what the theta is from some other procedure. You might have picked another estimator and get a reasonably decent guess for what theta is. Start with that and hope that that's close to the global minimum. In general, however, you won't know. Okay, this is just one of the facts of life. When you solve these kinds of estimation problems, you won't know if you've hit the global minimum unless you do a lot of playing around with these kinds of things. Okay. Another nice thing about this is that you can play small games with this, like instead of H transpose H, you can put this H transpose H plus some lambda times identity and then play with the lambda to make sure that the iterations don't kind of become stagnant. Right? You can accelerate the convergence by putting some coefficients inside this and so on. Okay. Which is something that's harder to do with the Newton-Raphson iteration, because you really don't have a lot of control. And if you go back to this, this is just, it is what it is. Okay. And it's not linear in the way that this is. Okay, so as I said, you can do this for one step. You can get an estimate for theta hat. And then if you want to do this in a sequential way, then there's going to be another update that you have to do. So once you've done all of these iterations, what do you end up with? You end up with a theta hat, which is the theta hat corresponding to the first n data points. Right? Now if you want to update your theta for the next data point, you have to do everything that I showed you for the sequential least squares, including the linearization. So there's going to be two iterations you're going to be dealing with. One is going to be the iteration to get the convergence here, and there's going to be another iteration which updates the estimate from theta hat n to theta hat n plus 1. Okay? So that's why I'm using a different index here. Okay? So this is what we call an inner iteration and an outer iteration. Okay, one last, a couple of last words about nonlinear least squares. There's other techniques for dealing with nonlinear least squares problems as well. One of them, which comes up very often, in fact, in engineering problems, is the so-called separable nonlinear least squares. So this is when you have a very special kind of problem where the expression for S of theta can somehow be broken up into two pieces that simply multiply each other. So let me give you an example. So let's say we have a bunch of data expressed as follows. Let's say A1 r to the n plus A2 r to the 2n plus, you could have a bunch of other terms too, it doesn't matter, e of n. Okay, and let's say we have n equals 0 to n minus 1. And I'm going to say the unknowns are A1, A2, and R. Okay? It's the classic problem that comes up in all kinds of engineering applications. This is called an exponential fitting problem. So for instance, you might have, these R's might in fact be complex exponentials, right? E to the j omega. This kind of formulation will then capture, it can be used as a model to describe multiple waves hitting a sensor. Okay? If these waves are coming from different angles, then these R's might even be different. Okay? But exponential fitting is a classic problem that comes up all the time. So let's see, how does this give us a particular type of least squares problem? Obviously, this is nonlinear because if only A1 and A2 are unknown, it would be a linear problem. Right? We've done this before. But because R is also unknown, then it's a nonlinear problem. So let's see how we can write this. So let's write all of our data. X0, xn minus 1. And this is 1, 1, r squared, so on, r to the n minus 1, r to the 2 n minus 1, times a1, a2, plus n. Okay? So let's call this the parameter vector A. And this is h, except that it contains an unknown. I'm going to call it h of r. Okay? So now if I write this whole thing, I have x equals h of r times a plus e. Right? So now if you think of this as s of theta, right? It's got all the s's and all the thetas in it. The theta here is a and r concatenated. Except that I'm able to write in a very special way. I'm able to separate the parameters into a group which contains the linear parameters and a group which contains the nonlinear parameters. Okay? This is called the separable least squares, separable nonlinear least squares. Okay, so why is this special? Okay, so let me write. So this was for this particular example. So let's write it in a much more general way. Generally, what you might end up with is a formulation like this. So h of alpha times beta plus error. And so the parameters of interest are the betas and the alphas. These are the linear parameters. These are the nonlinear parameters. Okay. So what do we do when we set up a least squares problem? Let's write j, and I'm going to separate this to j of alpha and beta. And this is going to be x minus h of alpha times beta transpose x minus h of alpha times beta. Okay? All right, so what we're going to do now is just to play a trick. Namely, we're going to first assume that alpha is known. Okay? So we're just going to fix it. Pick a number, fix it. Okay? And solve this as if it was just a linear least squares problem. Okay, so fix, or let's say assume, a given alpha, solve for beta, meaning minimize this guy as a function of beta. And of course, when you do that, you get beta hat is h transpose alpha, h alpha, this whole thing inverse, h transpose alpha times x. Okay? Now what we're going to do is we're going to take this beta hat and we're going to plug it into this quadratic term. Okay? And what we're going to get is j alpha beta hat becomes x transpose I minus h alpha h transpose h inverse h transpose times x. Okay? Now this ought to be looking a little bit familiar. If you remember before when we talked about projection matrix, it turns out that this term here is in fact the projection matrix, and so is I minus that. So if you have a projection, just a complementary projection is I minus that. So what's happening is that by virtue of picking an alpha and solving for beta and then plugging it in here, we've turned j into an expression which is basically the projection of x onto the subspace of signals spanned by the columns of h of alpha. Okay. Now what we can do is we can try to minimize this cost function over the space of alphas. And this should typically be a lot easier than simultaneously solving these two. Okay, so let's see. Oh, yeah.
And do we have the optimal answer in this case also?
What do you mean?
I mean,
do we get the right answer?
Yes.
Okay, I'll describe that in a second. So it turns out some technical conditions have to be satisfied in order for you to get the right answer. So let me take a couple more steps and then I'll try to answer that question a little more in detail. So remember, what we want to do is minimize this, right? And the equivalent thing to minimizing this would be maximizing it without the I minus. Okay, so let me just write that down. So equivalently, you maximize over alpha X transpose H alpha. Okay, and you get your alpha hat, and then what you can do is take this alpha hat and write beta hat as H transpose alpha hat H alpha inverse H transpose alpha hat X. Okay, this method is called variable projection. Okay, and there's a classic paper on this. There's actually a relatively recent version of it as well, which sort of summarizes all the applications of this by Golub and Pereira. Okay, so if you want to learn more about it, look up variable projection. Now let me get back to your question about whether you get the right answer. It turns out that if this function here is differentiable 2 times, okay, meaning that it's sufficiently smooth, then this procedure that I just described here will give you exactly the right answer. There's a couple of other technical things that have to be satisfied as well. Then this procedure will give you exactly the right answer, just as if you had simultaneously minimized beta and alpha. Okay? Now, if those technical conditions are not satisfied, then people do something a little different. Namely, they just alternate between alpha and beta, alpha and beta. They keep doing it. Okay? Here, you're not alternating at all. You're just doing it once. Okay? In fact, in practice, this beta is not good because your alpha at the beginning was just a dumb guess, right? You don't in fact do this in a numerical sense. You construct this matrix or this quantity and then differentiate it and solve, symbolically differentiate it and solve. So you never start with a beta hat. You just use the expression for beta hat to reduce it to this form. So the algorithm is basically you first minimize this guy with respect to alpha, you get an alpha hat, and then you plug it into this equation, you get to beta hat, and you're done. Right? So there's 2 other things you can do if these conditions are not satisfied and you're not getting the right answer. You can simply do alternate minimization, and you don't have to do this the way I said it. You can simply take J, okay? You can simply take J and fix beta, or sorry, fix alpha, solve for beta, then go back and forth. Okay. In general, there's no guarantee you'll even get convergence. Okay, let alone the right answer. Okay, that's called alternate minimization because you're just switching back and forth. Now, there's another set of things which don't require you to have a separable problem. In fact, you might have alpha and beta just in 2 pieces inside the S. There are another set of algorithms called expectation maximization algorithms, or EM algorithms. Again, some certain set of technical conditions have to be satisfied for those to also converge. And in those cases, there's a proof of convergence and you'll get the right answer. Okay. Somewhat surprisingly, this variable projection is virtually unknown in both electrical engineering and in computer science. So if you have a problem that you think could use this, if you use it and if you can check to see if the conditions here satisfy, look in this paper, you'll immediately surprise the reviewers, as they won't even know about this. What's variable projection? This is typically I've used it in several of my papers and with great results. The other 2 things that I mentioned, the EM algorithm and the alternate minimization, are the most popular tricks that people in EE and CS use to minimize things like this. Okay. So I don't know, that's probably not a complete answer to your question, but again, this is a very sophisticated set of results. Look up this paper, and if you have questions, I'd be happy to answer them for you. Okay. So I'm going to stop on least squares. So the next half an hour I'm going to spend talking about going back to hypothesis testing problems. But now we're going to assume that we're going to put to work all the stuff that we've learned about estimation in situations where you're doing hypothesis testing and there's a bunch of parameters that you don't know. Okay? And now we know how to estimate them. We can estimate them using least squares, maximum likelihood, maximum a posteriori, and a bunch of other things. Okay? So once I'm done with the composite hypothesis testing, then I'm going to come back to estimation and show you even more sophisticated ways of solving estimation problems, like minimum mean squared error, and the Bayesian minimum mean squared error, not the kind that you've seen already, and non-parametric techniques. So those are the more advanced things, and the last couple of lectures of this quarter will be dedicated to those. Okay, so any more questions so far about least squares, which has occupied us the last couple of lectures? All right. Okay, so we're going to start talking about composite hypothesis testing. And the reason we call it composite is simply because there are some unknown parameters in this scenario. So this is detection of signals with unknown parameters. It turns out as soon as you have unknown parameters in the signals you're trying to detect, the problem gets a whole lot more complicated. Okay? If you have unknown parameters, that basically means that essentially the PDFs for H0 and H1 are not exactly specified, right? So let's just take the case where you have, as an example, let's say x of n is equal to a plus noise, okay? And suppose you want to detect whether the signal is present or not and you don't know a. Okay, so remember, suppose this is just normal, zero mean, unit variance IID. Then P of x given H0, this is Gaussian with mean 0 and covariance sigma squared identity. And P of x given H1 is n, a bunch of 1s times a, sigma squared identity, right? So now if a is not known, then the PDF in this situation is unspecified. I mean, it's specified in the form, but you don't know something about it. And so you can't just do the standard thing that we did before with the likelihood ratio test. So how do we proceed? Well, generally speaking, there are two particular ways to proceed. So two approaches. One of them is what we call the Bayesian approach. And the idea here is that what you're going to do is you're going to take your unknown parameters, but you're going to assume that you somehow have some probability density function for those unknown parameters. Okay, so this is like we did before, right? When we did maximum likelihood, we assumed we didn't know anything about the parameter. When we did maximum a posteriori, we assumed we had a probability density for the parameter. So here we do the same thing. Let's see, unknown parameters have known PDFs. And then what we end up doing is we say, okay, since they have a known PDF, let's get rid of the effect of these unknowns by simply looking at the expected value with respect to that distribution. Okay? So what it ends up requiring is for you to do an integration, as you'll see in a minute. So the second one is what we call generalized likelihood ratio test, or GLRT. What this approach does is you explicitly determine the unknown parameter. So the advantage here is that you in fact estimate the unknown parameter given the data, and what you can do is then take that estimate and plug it into the likelihood function and then do a standard likelihood ratio test. And of course, immediately the question that should pop to your mind is, why is that a good idea? Right? Does that give you the optimal detection? And the answer is no, it doesn't. Except in some exceptional situations. In general, it turns out there is no proof that the generalized likelihood ratio test will give you the optimal answer. However, in almost all practical situations, it tends to perform near the best thing you can do. But nobody has been able to prove a general result that says GLRT is a good thing to do in every situation, in the way that we can prove for the Neiman-Pearson result. Neiman-Pearson is airtight. It says if you do this, you maximize the probability of detection for a fixed false alarm rate. When you do GLRT, you cannot prove a general result like that anymore. Okay? So let me be a little more specific. So let's say you have two hypotheses, H0 and H1. Here you're going to have a PDF, X given H0 and theta 0, some parameter. And here PDF of X given H1 and some other parameter, theta 1. In the example that I just gave you, there was only one parameter that was unknown in the second case. There was no theta 0 in this case. But in general, you might have unknown parameters in both cases. Okay. And so theta 0 and theta 1 are unknown. Okay, so then these two different approaches that we talked about work as follows. So let's talk about the Bayesian one first. So in the Bayesian approach, we assume that we have two PDFs, P of theta 0 and P of theta 1 are given. All right, so then what we do is we write this P of X given HI theta I, and this I here is just 0 or 1. Okay? And what we want to do is we want to get rid of this theta. So we want to turn this into P of X given HI without this theta I. Okay, well the easiest way to do that, or really the only way to do that, is P of X given HI is the integral P of X given HI and theta I times P of theta I d theta I. Okay? Basically, we marginalize the unknown parameter. We use the fact that we know something about it. We just get rid of its effect by integrating it out. Okay? Now, once you've done that, then you're going to get these guys, and then you're going to write P of X given H1, P of X given H0, and you're going to compare this to a threshold, H1, H0, and this is just your Neiman-Pearson likelihood ratio. Okay? What are the optimality properties of this? Well, at this stage, it's optimal, right? So in this case, I know that if I marginalize the two densities and get rid of the effect of theta 1 and theta 0, this will now maximize the probability of detection for a given false alarm rate. However, the problem is that I have picked a prior which may not be exactly right, right? So it's really the difference between, do you trust the data or do you trust your prior? Okay? So I can pick some prior for theta 0 and theta 1, and if I make a slight error, then what I've done is I have biased my decision towards one side versus the other. And even though I do this integration, that effect doesn't go away exactly. And so this marginalized PDF, even though it gives the appearance of being optimal, you may in fact be biasing yourself away from the truth. On the other hand, the GLRT approach always relies on the data, even though you can't prove a general optimality result for it. Okay, so the problems with this, again, the subjective nature of the choice of the prior, but also probably the most complicated thing about this approach is the calculation of this integral. Okay. Now, it looks simple enough, but remember, theta I might not be a single parameter, right? Theta I, which is unknown, might contain several unknown parameters. And this integral may be very, very complicated to calculate. So let's say, pick a simple distribution for P of x, let's say Gaussian. But what about this guy? Suppose that this guy has a, let's say, Laplacian distribution. Right, so now you've got a Gaussian times a Laplacian integrated in multiple dimensions. Not an easy thing to do. So you have to resort to numerical techniques, like what I said, Markov chain, Monte Carlo, and so on, for marginalization to get these guys, and then to try to normalize. This is not a trivial thing to do. This is something that we don't generally like to do in practical, at least in EE applications. In many other applications, people do because they trust their priors, and they don't mind doing a lot of number crunching to calculate these things. But in general, the more popular thing to do, certainly in EE applications, the signal processing applications in particular, is to do the generalized likelihood ratio test. So let's describe exactly what that is. So likelihood ratio test, this is L of x equal to P, x given H1, P of x given H0, compared to a threshold, H1 and 0. Okay? GLRT, we like to write the likelihood function as L sub g for generalized x. This is P of x given H1, theta 1 hat, P of x given H0, theta 0 hat, compared to a threshold, H1 and H0. And theta hat I are the maximum likelihood estimates. Okay? Now, you might say, well, why maximum likelihood estimate? Why not use something else? Why not use least squares or maximum a posteriori or something else? You can. Okay? Then you can't call it generalized likelihood ratio test, because the definition of GLRT is substituting maximum likelihood for these things. And people have studied the GLRT for a number of years, and there's been many results that have been proved about it. Not the one that we really want, which is that it's optimal, but many other results, many other very useful results. And they all depend on the assumption that you're plugging in the maximum likelihood. Okay? So if you plug in something else, there may not be a result out there in the literature that tells you how it's going to perform. But it's not, there's nothing here that stops you from doing that. Okay? Okay, so what are some of the advantages? Well, obviously it's simple. It's certainly simpler than doing a high-dimensional integral. You can also get the parameter estimate as a side benefit. Maybe you want the value of theta hat in these two cases as well. And as it turns out, there are some asymptotic optimality properties, but no general optimality properties. So these are advantages, and I would say disadvantage. The major disadvantage is that there are no general optimality properties. Okay, another way to write this, by the way, I should say, is g of x is basically you're doing max over theta 1 p of x given h1 theta 1 divided by max over theta 0 p of x given h0 theta 0. Okay, because that's the definition of maximum likelihood. All right, so let's do an example of how this works. So let's say we have two hypotheses. Under H0, X is W, which is normal. 0 mean, sigma squared identity. Under H1, X is H times theta plus W, where theta is unknown. So just to intuitively describe this, what this says is that the signal, it is known to live in a space, which is the columns of H. But it's not known exactly which signal it is. Okay, so you see kind of basically the signal is partially specified, but not exactly. So for instance, it might be interesting to define the space to be the class of functions that you're interested in getting. Maybe these are sparse functions or something like that, and then you pick a particular H. But you don't know exactly which signal you're looking for. So now if we set up the generalized likelihood ratio test, what we have is in the numerator p of x given h1, and now here the theta is not known, so we say theta hat maximum likelihood divided by p of x given h0. Okay, so let's write this out more explicitly. It's the exponential minus 1 over 2 sigma squared x minus h theta hat ml transpose x minus h theta hat ml, and then in the denominator minus 1 over 2 sigma squared x transpose x. And the coefficients in front of these just cancel each other out, so I don't need to worry about it. And so this is the generalized likelihood ratio. And now I'm going to simplify this by taking okay, so this is going to be compared to a gamma, right? So I'm going to take log of this and simplify, and here's what I'm going to get. Minus x minus h theta hat ml plus x transpose x compared to 2 sigma squared log of gamma. And this is the gamma that we just had before. Okay? Now I know that theta hat maximum likelihood is h transpose h inverse h transpose x, which happens to be the least squares as well. So what I'm going to do now is I'm going to take this, plug it in here, expand the whole thing out, simplify, and see what I end up with. Okay? So let's do that. So replace in here. Okay? And when we do that, I get minus x transpose I minus h transpose h inverse h transpose x plus x transpose x compared to, let me just call this gamma prime. Okay? Just some other threshold. Okay, so if you look at this, here there's a minus x transpose identity x, so that's going to cancel this guy. Okay? So what we're going to be left with is X transpose H, H transpose H inverse H transpose X compared to gamma prime. Right? Now, we've seen this many times now. This is a projection matrix. Right? So what does this tell you? It tells you that the detector that you have is basically looking at X, projecting it onto the space spanned by the columns of H, and then looking at the magnitude. So to write that out, so this is your test statistics, right? T of X, this is X transpose Px, which, because this is a projection matrix, I can write it as X transpose Px. And so this is Px transpose Px, which is the norm of Px squared. So your detector is norm of Px, I need the parentheses, Px squared compared to some threshold, right? So here's the space spanned by the columns of H. Here's your X. What you're going to do is you're going to project it down like this. This is Px. Then you're going to look at the magnitude of this guy and compare it to a threshold. That's your detector. Okay? This is the generalized likelihood ratio test detector. What's interesting about it is that it is using knowledge of the model. So remember what we said. This is basically telling you, you know something about the signal. You know that it lives in this particular space, but that's all you know. You don't know which particular signal it is. So what the detector does, says, okay, since I know the signal lives in this space, I'm going to take your measurement, I'm going to put it in that space, and I'm going to compare its energy to a threshold. If the signal is present, that threshold should be exceeded. Okay, the projection ought to be large. If there's no signal, if I take this X and I project it down to the space, all I've done is I projected noise down into the space. I should get nothing special. I shouldn't get a lot of energy. And so therefore you probably won't exceed the threshold in that case. Okay? All right, so one of the things that may be a little bit confusing about this is the fact that in this formulation, we are going to replace this theta hat maximum likelihood with this expression, where in fact it looks like we are implicitly assuming the signal is there, right? I clearly told you there's two hypotheses, right? But what if you calculated this and X happened to come from this hypothesis? Right? What would happen? Of course, your estimate of theta hat maximum likelihood would just be ridiculous, right? It would be meaningless, because all you're doing is you're plugging noise into this expression, right? It turns out there's nothing wrong with that, because that's exactly what the GLRT does. If there's no signal, then this estimate will be wrong, but it will be wrong in such a way that it will make this number small. So that's okay. Okay? This is, I would say, the most common question and the most common source of confusion about the GLRT. Why should I write this down when I don't know which hypothesis the X is coming from? The beauty of GLRT is that it doesn't matter if you don't know. If you don't know, it does the right thing. If you do know, it does the right thing. Okay?
Excuse me?
Yeah.
What happens if both of these vectors have the same projections on the plane?
Both of these vectors have the same projection. Then you've become very unlucky. Right? The point is, it is with probability almost 1, that's not going to happen, right? Because you basically have the same W here, right? And this term here The only time they're going to have exactly the same projection in that space is if this term is either 0 or very, very close to 0. Okay? And if that happens, it means that your signal-to-noise ratio is so low that you don't really have any business detecting the signal anyway. Right? So suppose, for example, theta is a really, really small vector. It has a very, very small magnitude. Then it's really going to be very difficult to tell these two apart anyway. So it's possible, but probability of it is exponentially small. All right, the performance of this detector, of course, is going to be different and specifically worse than the case where theta is known, right? So let's, if you have this problem x equals h theta plus w, this is under h1, and under h0 you have x is w, again it's the same thing. If theta is known, then the performance that we had was okay, so in this case, you're going to get a Gaussian, so x is going to be a Gaussian with mean h theta and covariance sigma squared identity under h1, and x is going to be normal with covariance with mean 0 and covariance sigma squared identity under h0. Okay. Now, the performance you would expect it to be worse in this case. And it turns out that can be, in fact, specifically studied. So in the case where theta is known, the detector is Tx equals x transpose h theta. Okay? It's just the, so if you call this S, it's just the matched filter. Right? So with this, then your T of x, your test statistics for the theta known case is like this. Under h0, T of x is Gaussian with 0 mean and covariance and variance sigma squared theta transpose h theta. And under h1 is also Gaussian with mean theta transpose h theta and the same covariance, sigma squared theta transpose h theta. Okay? So here we could, for the known for the known theta case, we could specify this performance. We have two Gaussians, then we can plot the receiver operating characteristic, we can plot the ROC curve, and it would look something like it would look something like this, right? This is 1, 1. Okay. Now, what about in the case where we don't know theta? When we don't know theta, your test statistic is a little different. This is x transpose px, right? Now, in this case, x is a Gaussian depending on, in both cases, x is a Gaussian, right? In this case it has non-zero mean, and in this case it has 0 mean. So what you have here is the inner product of two Gaussian vectors. So this turns out to be a chi-square distribution. And the number of degrees of freedom that you have are related to the rank of P. And the rank of P is the number of unknown parameters that you have, which is little p. Okay? So with this, you have the following densities. The test statistic for the generalized case, this is going to be a chi-squared with p degrees of freedom. And in this case, it's also chi-squared with p degrees of freedom, but it has something called a non-centrality parameter because the Gaussian you started off with is not 0 mean. And it turns out that this non-centrality parameter is 1 over sigma squared theta transpose h theta, which is basically the signal to noise ratio. Okay? So you can think of this as S transpose S divided by the variance of the noise. Okay, so if we were to take this now, so now we can specify the performance of both cases. In this case, it was a theta known, and in this case, is the performance with theta is not known. And if you were to go to MATLAB or something and plot this, what you will see is this case, where theta is not known, will look something like this. Okay? The rock curve will be below the rock curve that you had. And how much below will simply depend on this non-centrality parameter. Yeah?
Lambda contains theta.
Lambda contains theta, that's right.
Theta is unknown. How?
That's right. So if you want to study the performance, what you have to do is you have to calculate this across lots of different values of theta. So for instance, I might ask you, what's the performance of this GLRT? And what you come back to me with is, if theta is equal to 0.1, this is what the curve looks like. If theta is equal to 2, there's another curve. So what you're going to do is you're going to plot this guy as a function of all the different thetas and show me a whole bunch of curves except for instead of just one. Why is that an okay thing to do? Because what you'll be plotting is basically the performance of the GLRT as a function of different signal-to-noise ratios. Right? So in fact, even if you don't have exactly theta, what you have in the numerator is basically just a scalar. Right? So just take that scalar and sweep it from 0 to infinity for a fixed sigma squared and plot a bunch of curves for me. And just come back and report to me that I don't know what theta is, but here's the performance of this detector across all these signal-to-noise ratios. Does that make sense?
Then how should we compute theta to compute chi-square distribution?
Well, like I said, you can take this to be any scalar you want. Okay, theta transpose H theta. If your objective is just to draw a rock curve.
But we need to compare with the previous case, so we need to know the exact value of theta.
Right, but remember, even in the previous case, you're assuming that you know theta, right? So if you want to compare it to the previous case, then use the same theta as you compared in the previous case in here and plot the performance. That's why I'm plotting here. So these two curves I'm plotting are for the same theta. Does that make sense?
Yeah.
Okay. So both of these are for the same theta. But this is a good point, because oftentimes what you will see is that the performance analysis that you will do for any detector, whether it's likelihood ratio or generalized likelihood ratio, will depend on the parameter value which you're trying to estimate, right? So then the answer to the question of how well does this estimator perform, the answer is not just a simple answer. The answer is, well, it depends on the underlying parameter. If the parameter is really small, then it's going to perform not that differently. If the parameter is really large, then it's going to perform differently. You see what I mean? So that's something that it just depends on the specific problem. In this case, the parameter that gives you this performance difference depends on the square of theta. In some other cases, it might be a very different function of theta. Okay. All right, so we'll stop here. Next time I'm going to do a few examples of this GLRT, and then also show you cases in which GLRT happens to be the right estimator to use, and it happens to be optimal in some specific cases. Okay? All right. So don't forget there's a homework due next week as well.